Hey everyone, so today I'll be talking about an asymptotically optimal algorithm for maximum matching in dynamic streams. This is joint work with Sepehr Assadi at Rutgers University. So what is the matching problem, right? So given a graph G, a matching is just a bunch of edges that don't share any endpoints. And the maximum matching then is the matching of the largest size. So the one with the maximum number of edges. So we're given an example graph here. M over here is a matching of size 2, but there's a larger matching here. M star, which is these three blue edges, has a size of 3. The setting we'll be looking at is the streaming setting, where the information comes in a stream and you can only look at the current bit of information and you have to update the memory using that. And once this information goes ahead, you are no longer able to access it. In our context, we'll be looking at the graph streaming setting, where the edges of the graph appear in a stream and the vertices are fixed from 1 to n. The edges can be inserted or deleted since it's a dynamic stream. So let's take an example and let's look at how this looks. So this edge is inserted, then this one, and so on. And then now you see this red edge means that this is an edge deletion. And this is finally what your graph looks like. So now, what is the goal of the setting? The goal of the setting is to minimize the amount of memory. And we want to output a solution at the end of the stream. So note that you don't have to maintain a solution throughout the stream. Okay, but unfortunately, the matching problem has a lower bound of n square. And the trivial solution is to store the input, store the entire graph in n square bits. And so there is no non-trivial solution. And when we have such lower bounds, we usually look for approximations. So the question is, what about an alpha approximation, right? Return a matching M of size at least M star over alpha, where M star is the maximum matching of the graph. Can we get a little of n square space? The trade-off between alpha and the space is the question we want to answer. So let's look at some previous work that is on this problem. Conrad 15 gave an upper bound of n square over alpha square and a lower bound of n to the 1.5 over alpha 4. And you see that the gap over here is alpha square times n to the 0.5. Assadi et al. Improved this gap significantly just to n to the little o of 1. The upper bound is n square over alpha cube, and this O tilde here is hiding polylog factors. And the lower bound is also roughly n square over alpha cube. Chittis et al. Also gave the same bound concurrently. And then Dark Conrad 20 gave a lower bound of n square over alpha cube bits. And now you see that the gap between the upper and the lower bound is just polylog bits, right? So the best known upper bound is O tilde n square over alpha cube bits, and the best known lower bound is n square over alpha cube bits. And the gap is polylog n. And these gaps frequently appear in dynamic streams, and the main reason for it is the technique we use to find edges in dynamic streams. And this is called L0 sampling. So the problem is to find just one edge in a dynamic stream, right? So you're given edge insertions and deletions, and you want to just output one edge at the end. And that problem itself is very non-trivial, because what if the edge you pick is deleted later, right? And L0 samplers solve this problem. And basically what they do is they sample an edge uniformly at random from a set of pairs of vertices that undergo edge insertions and deletions. Now, L0 samplers can be implemented in log cube n bits of space, but they also need log cube n bits of space. And many problems in streaming have this polylog overhead because of L0 samplers, especially connectivity, which has a lower bound of n log cube n bits. And this was given by Nelson U19. So this raises a question: is this always necessary, or is this polylog overhead always necessary? Now we present our result. We prove an asymptotically optimal bound of the space approximation trade-off. There is a dynamic streaming algorithm that with high probability gives an alpha approximation of the maximum matching. it uses n square over alpha cube bits, and it works for any alpha less than n to the 1/2. So this, as you can see, closes the gap up to constant factors. And also this shows us that polylog overhead is not always necessary. So this problem, the matching problem in particular, doesn't need this overhead. Also, you might be wondering why we consider alpha less than n to the 1/2. If alpha is greater than n to the 1/2, then there is not enough space to output the answer, because n over alpha, the number of edges needed, is greater than n square over alpha cube. So now we show how to prove this. So we first give some simplifying assumptions for this talk. The input graph is bipartite. The maximum matching has a size omega n, and getting an theta alpha approximation is enough. And note that all of these assumptions can be lifted. So now we look at the hard instances from previous work, Conrad 15, Assadi et al. 16, and Dark Conrad 20. All of them give certain versions of this hard instance. So the top part over here has little o of n over alpha vertices, and the bottom part has theta n vertices. Now if you look at any vertex in the bottom part, it is connected to most of the vertices on the top here. These squiggly lines indicate that every vertex here is connected to most vertices here, and same for this squiggly line. And if you look at any vertex here and delete all of the edges it has to the top part, it has just a single edge to the bottom part, right? And the lower bound of Dark Conrad 20 was n square over alpha cube bits using this hard instance. So now what is the approach we will be using to solve our problem, right? So we will first show this lemma called match or sparsify that either gives a large matching, in which case we're done, or it identifies a hard instance which is similar to the hard instances of previous work. And then what do? We solve this hard instance. And note that we run both of these algorithms in parallel. It might think that we're saying, oh, do match or sparsify first and then solve the hard instances, but they're actually happening in parallel. So what is match or sparsify, right? So we find a matching M easy in space n square over alpha cube bits, such that we either get a large matching of size roughly n over alpha, in which case we're done, or we get a matching M easy such that when we delete its vertices or look at the subgraph induced on its unmatched vertices, we're left with just O tilde n edges. And also we have a matching of size omega n within there. So if the matching is large, we're done. If the matching is not large, then this remaining graph, once you delete all these nodes, has O tilde n edges and a matching of size omega n. So how do we solve this problem, right? So we sample n square over alpha cube times polylog n random edges. Note that this polylog n is in the denominator. And we do this sampling using L0 samplers, which take polylog n bits. So this will give us a space of n square over alpha cube bits in total. And then the matching M easy is just a greedy matching over the sampled edges. And we use something which is similar to a residual property of the greedy matching. And it is alright to not know this because we will not be using it in the talk. But the proof is like along the same lines, but it is considerably different and interesting to look into. We will be skipping it for now because of time, and we concentrate more on the more novel parts of our paper. So we look at the similarity to hard instances of previous work, right? So our hard instances are qualitatively the same as the hard instances of previous work. So this part over here, which is the matching part, is similar to this top part here. Once deleted, you get this sparse portion over here, which is very similar to this. So there are theta n edges here and there are O tilde n edges here. Now we want to solve this hard instance, which is slightly easier to do. So first we will try to solve this one, and then we'll go to the general hard instance. This instance, once we apply the analysis of dark conda at 20, informally, we need n square over alpha cube edges to be recovered. This itself, storing these edges, is going to take n square over alpha cube times log n bits, which is more than our space budget. And using L0 samplers makes it even worse, makes this log factor into polylog n. So now we show how to get rid of this, and basically how to solve the problem in n square over alpha cube bits. So now we want to solve this hard instance. So first we use match or sparsify, and that basically gives us this partition of u and b of these vertices which have a very high connection, and these vertices that have just one edge to b. Right, so this partition we get at the end of the stream using match or sparsify. Now we look at our input graph. We look at the left side and we try to group it into groups of size alpha, and we do this partition randomly. Then we consider any group on the left, and with high enough probability it lies completely within B. Okay, so now we focus on one such group, and you see that this group will have many edges to this red part here because this is highly connected, but it has only alpha edges to this bottom part B. And this is because every vertex in this green part will have just one edge to B. So our idea is to recover one edge per group. So since we just need one edge, what we do is now we subsample with a rate of 1 over alpha. So basically for every group, we consider n over alpha nodes on the right, and we call it the neighborhood of Vi. Now the neighborhood of Vi will have just n over alpha nodes, and looking at these, little of n over alpha square come from U, and the remaining ones come from B. And now this is the one edge we want to recover. So it has just one edge to the green part and many edges to the red part, and this is the edge we want to recover. So this actually is the hard problem we want to solve, and basically the question is, can we get this one neighbor efficiently? And this looks like the set disjointness problem from communication complexity, right? Because we want to find a vertex such that it has an edge from Vi and it is also from the set B. And note that we get the set B at the end of the stream using match or sparsify. So a trivial solution to this problem is you can store everything, right? You store all the edges of Vi. So there are little of n over alpha square edges to the red part and one edge here. So you can do it in space n log n over alpha square bits. But the goal is to do it in n over alpha square plus log n bits and not times log n. And the reason for this is that this gives us a space of n square over alpha cube because the total number of groups are n over alpha. And this log n is a lower order term because alpha is much smaller than n to the 1/2. Good. So what is the idea? We represent the neighborhood vector Vi as a binary vector, and we compute the inner products with random vectors. So you can think of this as a sketch that we store. And using the sketch, we will recover the neighborhood vector. So what is the recovery? You go over all possible neighborhood vectors that could have been and check if the inner products match. If for any particular guess, all the inner products match, then that is the neighbor vector you were looking for. Now the number of possible neighbor vectors are 2 to the little o of n over alpha square times n. And this is because for a group here, you could have any subset of U within the neighborhood. So that gives you 2 to the little o of n over alpha square choices. And then this one edge could be to any vertex. So it is at most n choices. And this gives you a space of n over alpha square plus log n bits, exactly what we wanted. However, there is an issue here. What we got to know is the name of this vertex, but we do not know the name of the endpoint within Vi. So we cannot recover this edge. We just recover this endpoint. So basically we need the grouping on the right hand side as well to solve this problem. So you consider the bipartite graph again, and you group both sides this time randomly. Then looking at any group with high enough probability, it lies completely within B. So now we focus on one such group. Again, we know that for this group, we have alpha edges going to B, but we just need one edge. So what we will do is we will subsample again, and this time for every group, we consider 1 over alpha fraction of the groups on the right and call it its neighborhood. So for any group, Vi in particular, it has n over alpha square groups in its neighborhood. So the green groups lie completely within B, and the red groups are a mix of U and B, or either just completely in U. And this is the edge we want to recover. Note that there might be multiple edges between Vi and Vj, but with high constant probability, there is just one edge between Vi and Vj. So we want to recover this edge now. So the way we do it is we look at the neighborhood sketch of Vi and find this node U inside Vj. And then we look at the neighborhood sketch of Vj and find this node V inside Vi. And now we know that since there is just one edge between them, we get this edge and we can recover it. And now note that we can recover such an edge for a constant fraction of the groups. So that gives you a matching which is of size omega n over alpha, which is enough for us. So now we've solved this problem, but we want to solve a more general problem, right? And there are a few challenges. So if you look at this graph, there are only theta n edges in the sparse part. But over here, we have O tilde n edges, which is more. And the more annoying part is that we cannot bound the degree of vertices with a constant. So over here, the degree of vertices is just 1. But over here, they could be much larger. So some of them could have a super constant degree, and some of them could have a small degree. So now this gives rise to our sparse neighborhood recovery sketch. And this is the general sketch we will use to solve this problem. So we're given a graph G in a dynamic stream. We're given a set S known before the stream and a set T known after the stream. And the goal is to get n of S minus T. So in this picture, this is the set S we know from the beginning, and this is the set T we are given at the end, and we want to recover this moon-shaped region n of S minus T. We're also given a few promises that the size of T is at most A, and the size of this moon-shaped region is at most B. N of S minus T is at most B. Also, any vertex here has just a constant number of edges to S. Okay. So the trivial solution for this problem is just store everything again, right? For S, store all of its neighbors. And this will take A log n plus B log n bits, right? Because this N of S could be of size order A plus B times log n. A plus B, good. But now the goal is to drop this log factor because we don't really need to store the edges to T, right? Because we just want to recover the edges to N of S. So this seems like a valid goal to have. So we could use the previous ideas of inner products, but that gives us two problems. One is that you need exponential time for recovery. And the other problem is that the random bits needed is much more than the space budget. So we get rid of these problems using sparse recovery ideas. And it's slightly complicated, so we avoid it in this talk. So the space bound is A plus B log n bits, and this is theoretically optimal, right? So now we've shown how to solve these general hard instances. And the main tool we used is sparse neighborhood recovery sketches. And the space now is n square over alpha cube bits. So now we conclude. The first step was match or sparsify. We used n square over alpha cube bits of space, and we either get a large matching or we get a hard instance that is sparse and contains a large matching. Our recovery sketches can be used to solve these hard instances in n square over alpha cube bits. And note that we run both of these algorithms in parallel and get the final algorithm. So there is a dynamic streaming algorithm that with high probability outputs an alpha approximation to the maximum matching using n square over alpha cube bits of space. The lower bound of dark Conrad 20 is n square over alpha cube bits, making our algorithm optimal. The polylog n overhead of L0 samplers is not always necessary, unlike Nelson U19. And now these polylog n overheads are due to the use of L0 samplers, and you can see them everywhere in dynamic streaming literature. So now the question we pose is that can our techniques be used to bypass this polylog n barriers? And some problems we can think of are vertex cover, dominating set, and vertex connectivity. This is where I will end, and thank you so much for listening.